All right, let's talk about energy and work. So right here is an equation that shows us a change in energy, which is potential and kinetic energy of particles that are inside a system. So that delta, the triangle that we see here, that's just a change in. Anytime you see delta, what it signifies is a final whatever minus the initial whatever. And in this case, since it's E, it would be the final energy minus the initial energy. So where it ended, where it started. And then Q, this is one we're going to see a lot this unit, is heat that is transferred either into or out of the system. If the energy is transferred into the system, think about that. If energy goes into a system, what type of process is that? It's an endothermic process. And so an endothermic process would have a positive value. If the energy is being lost by the system, it would be negative, and that would be an exothermic process. And work, it's a little bit trickier because this is something physical that you do to a system. So work is done on a system like when you change the volume of a gas. So if you have a sealed syringe and you push the plunger down, you're doing work on that gas. Stirring, shaking, bouncing up and down, all those can be considered work. And once again, an endothermic process, energy flowing into the system would be positive. Exothermic, energy flowing out of the system would be negative. And that positive-negative thing always holds true for endothermic, exothermic, no matter what the values we're talking about. So heat, work, and later on enthalpy. If it's positive, that means it's endothermic. If it's negative, it is exothermic. And just buzzing right back to the first one real quick, PE versus KE, we talked about kinetic energy, that's motion, so things moving around, that's those particles vibrating or bouncing off each other. The PE, though, the potential energy, is associated with bonds, and so if you have a chemical with really weak bonds or really strong bonds, it's going to affect the potential energy, so they have potential to release a lot of energy. Think of single versus double versus triple bonds. Triple bonds have higher energy, so that would be high potential energy. Because when triple bonds break, they release a lot of energy. And so within an isolated system, so a system where nothing's really being affected from the outside, so no energy coming in from the surroundings, energy is always conserved. And so if we look at this example right here, we have a gas, and so that means those molecules are bouncing all over the place, which means high kinetic energy and lower potential energy. If it decomposes, though, into carbon dioxide and H2, that means it's going to have less kinetic energy and more potential energy. More potential energy is created because we had to put energy in order to create these different bonds. Where did that energy come from? Well, it came from the kinetic energy. So you notice how the potential energy increased and the kinetic energy decreased. It means it's conserved. So the energy in order to create that potential energy came from the kinetic energy. Overall, then, the amount of energy possessed by the system stays the same. However, this is an endothermic process because it contains more potential energy than it does kinetic energy. And so we had to put energy, or energy had to kind of be put into those molecules in order to create this new system. Now, if we take that reaction from before and instead surround it by things so it's no longer isolated, the temperature would be lower inside of the system than its surroundings. And if that's the case, then energy is going to want to flow into it. So when you feel something, you're not feeling cold flow to your hands, you're feeling the heat from your hands flow into the system. Since the energy here is lower, heat would have to flow to it in order to establish that equilibrium. Now here's an example of a combustion reaction. Once again, energy is conserved, so we see that methane and oxygen have high potential energy. So the bonds within these guys are very strong, and so that means there's lots of energy built into them. Kinetic energy, though, is lower with respect to the potential energy. After the reaction occurs, we've generated lots of kinetic energy and less potential energy. So these bonds don't have as much energy built into them. Once again, energy is conserved. This potential energy was transferred into kinetic energy, and so it wasn't like energy just came in and brought that guy up, and this just disappeared. It was transferred from one to the other. This process right here would be a negative and exothermic process. And since kinetic energy is what we feel as temperature, this is why a reaction like this would feel hotter to the touch or warmer to the touch, because there's more kinetic energy. So that higher kinetic energy then means it's going to be at a higher temperature than the surroundings, and so heat is going to be transferred from the system to the surroundings until that thermal equilibrium is established again. So when you feel something that's exothermic, the reason it feels hot is because the energy is being transferred from the system into your hands, which are the surroundings. So the term piston, we're going to use this a lot. And if you're not familiar with a piston, they're in your cars, and what it is a sealed container with a movable seal on top. And so that can slide up and down without really letting out any gas. So if you think of a sealed syringe that you push the plunger down, that would be like a piston. So you're not really letting anything in or out, you're just changing the volume. And so if we have a gas inside of a piston and a gas outside of the piston, if the pressure from the gas outside is greater than the pressure on the inside, the gas on the outside will push down that piston and shrink the volume. And what this means then is that work is being done on the gas on the inside. So if the inside is our system and this is the surroundings, work is done by the surroundings on the system. So in this case then, work would be positive. It is an endothermic process. If we reverse this same idea and say that the pressure on the inside is greater than the pressure outside, that means the piston will move up. When that happens, that means work is being done by the system on its surroundings. And so in this case, work would be a negative number. The good news is the only work we're going to talk about in this course is going to be volumes of a gas. We're not going to talk about any of the other changes that involve work. This is just the most common one and the one that's most relatable to chemistry. And if we want to talk about just work for a second, work is equal to force times the change in distance. And so if we push a piston down, the change in distance would be that difference right there. And if you want to nerd out for a second on deriving equations, we can convert this into something useful for gases, knowing that pressure is force divided by area, and a change in volume, so the change in what we're covering there, if this is a three-dimensional object, would be equal to the area times the displacement. And so if we take those values then and plug them in for the equation, so force would be the same thing as saying pressure times area. And then over here we can see that area times change in displacement is equal to the change in volume. And so we could take those values and put them together. And in order to get the correct sign for endothermic and exothermic, we would need to make the overall value negative. So that'll adjust it to the right value. So overall, if you're not big on the math part, this is just what you need to know. So work is equal to the negative pressure times the change in volume. Alright, let's try an example. So here we have a gas that expands from 0.87 liters to 2.46 liters. It's in a cylinder, so a piston is going on, and there's a constant external pressure of 1.05 atmospheres. And so here's what this would look like. We have our gas on the inside, the piston is going to go up, and so the volume will increase. The pressure on the outside is staying constant, so we have 1.05 atmospheres before and 1.05 atmospheres after, and that's what's pushing down on the piston. Obviously, we have a greater pressure on the inside, and that's why the piston moves up and overcomes this. At this point, though, when the piston stops moving, that means the pressure inside is equal to the pressure outside. And so we know then that the pressure in here afterwards is also 1.05 atmospheres. And let's predict right now what should our sign be for work after we finish this. Since work is being done by the system on the surroundings, we should wind up, if we do our calculations right, with a negative value. So let's go ahead and test this out then. We know that work is equal to the negative of the pressure times the change in volume. And pressure is 1.05 atmospheres. And the change in volume then, remember, change in anything is equal to the final minus the initial. And so in this case, our final volume was 2.46 liters, and our initial volume was 0.87 liters. And so to get the delta V, we just subtract final from initial. And the value that we get for work then is 1.67. And units on that, we're multiplying atmospheres by liters, and so our units would be atmosphere times liters. Work, though, is measured in joules, so we do have to convert those units to something more useful. And the conversion from liters, atmospheres into joules is 101.3 joules for every liter atmosphere, atmosphere liter in this case. And so those will cancel out, and we get our final answer as negative 169 joules. And so this is good. We see that our sign does match. We wind up with a negative process because work is being done by the system on the surroundings. And so the amount of energy that is transferred then would be 169 joules, and it's being transferred from the system to its surroundings. All right, here's another example. Why don't you pause the video and give this one a shot yourself? So this does use the work equation, and it also used that first equation, the delta E one. That's just kind of a heads up. Go ahead and pause the video, try this one out, and resume the video to check your work. All right, here's a pictorial of what's happening then. We have a cylinder that's down low, and then it goes up higher, so the piston does move, and we are supplying energy to this, causing the piston to go up. Now, predicting the sign is going to be a little bit tricky for this one, because if we look right here, we are supplying heat to the gas, which means that is an endothermic process. We are transferring heat energy into that right there, but work is being done by the system on the surroundings because that piston is moving up. So we would have a positive value for the heat energy, but we would have a negative value for the work energy. So then predicting the overall sign is going to depend upon the magnitude of those two. Let's go ahead and work through the calculation on this one. And the overall equation that we're going for, we're looking for delta E, and delta E is equal to the work, or the heat, plus the work. And we already have the heat. We say that there's 1142 joules of heat added to the cylinder, and since it's being added to the cylinder, that means it is a positive 1142 in our equation. Now, if it was 1142 being put from the cylinder to the outside, they're not going to tell you negative 1142. That's something you have to be able to distinguish yourself. But in this case, it's positive. Work, though, we're going to have to calculate that using the equation we just saw. And so negative of the pressure, 1.05 atmospheres, and the change in volume is going to be 4.18 minus 1.35 liters. And so then we would come up with a work value of negative 2.91 liters atmospheres, but we need to convert that over using the conversion that we saw before of 101.3. So what that means then is our work is negative 295 joules. And this should make sense because work is being done by the system on the surroundings since that piston is moving up. Negative value means it's releasing work. So now let's combine our two values to get the delta E. So our heat is going to be positive 1142 joules. And we're going to add that to the joules from the work, which is negative 295 joules. What we can tell right away then is the magnitude of the energy supplied by the heat is greater than the magnitude of the work done by the system. And so overall, our delta E is going to wind up being a positive number. And that positive number is 847 joules. What that means then is this entire process is an endothermic process. It's positive, which means that overall energy was put into the system. So in order for this process to occur, energy was needed to be supplied from the system to the surroundings, and it was supplied in the form of heat.